Okay, let's continue with our transform of important functions, and we are going to see the Laplace transform of a ramp function. So a ramp function is defined by t, and because we are interested in the time interval starting from 0, so we are going to attach that u at t, because a ramp function essentially is a t function which starts from minus infinity and goes to infinity, but we are interested more in the positive term, and that's what we do in circuit analysis. So that's why we are attaching that u at t. So what is a Laplace transform of a ramp function? So in order to compute the Laplace transform of a ramp function, we will use our definition, which is integrating from to infinity of t. So if we limit our integration from 0 to infinity, then we don't need to write u at t. If we write it, it's okay, but this is essentially because that part is 1, then this integration can be rewritten as t e raised to minus st dt. So in order to solve this integration, we go to integration by parts method, which is done by, if we have to integrate u dv, then integration by parts tells us that that can be split into 2, which is uv minus the integration of dv u dv minus okay, I think that one is u dv is equal to uv minus v du. Yeah, so in that case we have u as t. Let me use another color. So u will be our t and dv will be our e raised to minus st, in which case du is going to be 1 and v is going to be minus e raised to minus st over minus s. So from this, integrating t e raised to minus st dt is going to be uv, for which we have t, and v is e raised to minus st over minus s. Don't forget to integrate it from 0 to infinity, minus the integration of v is e raised to minus st over s, and du is 1, so we'll integrate that. So what does this give us? Here, if we replace infinity in the place of t, then that thing will go to 0, so we don't care about anything else. 0 minus, if we replace 0 here at t, the whole thing will be 0. So we have 0 minus 0, which is 0, minus, in this case v was minus s, right? So that should give us plus e raised to minus st, and we can bring s here, dt, from 0 to infinity. So we know that that part, when integrated, should give us 1 over s. So we have 1 over s multiplied by minus 1 over s e raised to minus st from 0 to infinity. And when we replace infinity here, we have 0. And when you replace 0, we have 1, which gives us basically 1 over s multiplied by 1 over s, which is 1 over s squared. So we have the Laplace transform of a ramp function t u at t, which is ramp function still, but this is to limit it from 0 to infinity, have 1 over s squared. So that is the Laplace transform of TUST. So far we have seen the definition, the singularity functions, u at t and Dirac, and the constant, and now we just saw the ramp function, and we are going to see the exponential, the Laplace transform of the exponential function. So when we compute the Laplace transform of the exponential function, which is e raised to minus at Then according to our definition, it should give us 0 to infinity e raised to minus at e raised to minus st dt, right? And that can be rewritten as 0 infinity e raised to minus s plus a t dt. And that is going to give us minus 1 over s plus a, because that's a coefficient here, and that's going to give us e raised to minus s plus a t to be integrated from minus infinity to from 0 to infinity. So what does that give us? When we replace 0 here on t, or let's start with infinity. When we replace infinity, e raised to minus infinity is going to be 0. So we have minus 1 over s plus a, 0. That part is going to give us 1 because infinity e raised to minus infinity is going to be 0. So we have 0 minus. When we replace 0 here, that part is going to have 1. So we have that value 1 over s plus a. So that part e raised to s plus a as a function of time, when time is replaced by 0, that whole part is going to give us 1. So we have that 1 here, and that would ultimately give us 1 over s plus a. Therefore, the Laplace transform of e raised to minus at is going to give us 1 over s plus a. And why is this function important? E raised to minus at is a decaying function, which is a more practical function than a positive. But just for the sake of it, if we are given to find the Laplace transform of e raised to at, where a is greater than 0, then that should give us 1 over s minus a, because now we are going to replace that. This is also another important function. This is a function which is basically underdamped, not practical, but there is a Laplace transform of that function. So we just saw the exponential function for that, or the Laplace transform for the exponential function. Okay, the next function that we are going to see in Laplace transform is two trig functions, which are the cosine omega t and the sine omega t. So we are going to see what the cosine omega, the transform of cos omega t is going to be. Before we start looking at the Laplace transform of cos omega t, there is one important property in Laplace transform that's called linearity. So linearity tells us that the Laplace transform of two functions, f1 at t plus f2 at t, the sum of, or the Laplace transform of the sum of two functions is the Laplace transform of f1 at t plus the Laplace transform of f2 at t. This gives us the Laplace transform of the first one plus the Laplace transform of the second one. Which means if we have to compute the Laplace transform of the sum of two functions, if we know the Laplace transform of each, then we just have to add that and it gives us the Laplace transform of the sum. So in this case, a cosine function can be written in terms of exponential functions using Euler's identity as e j omega t plus e raised to minus j omega t over 2, which means the Laplace transform of cos omega t is going to be the Laplace transform of each here, which is e raised to j omega t over 2 plus e raised to minus j omega t over 2, which would be Laplace transform of e raised to j omega t over 2 plus the Laplace transform of e raised to minus j omega t over 2. And that sounds familiar, right? This is the exponential function we have seen earlier. So if we have e raised to at, then its Laplace transform is 1 over s minus a, in which case if we have, so this is the same as 1 over 2 multiplied by the Laplace transform of e raised to j omega t has got to be 1 over, it has to be now 1 over s minus j omega, right? Just by using this relationship here. If we have minus 80, it will be 1 over s plus a. So in the place of a, if we replace j omega, then we'll have 1 over s minus j omega. By similar property, we have here e raised to minus j omega t. So in this case, we are going to have 1 over s plus j omega. So 1 over 2 is common here. We have 1 over s minus j omega plus 1 over s plus j omega. So if we simplify this, it will take us to s minus j omega times s plus j omega. At the top we have s plus j omega plus s minus j omega. And that is going to be multiplied by 1 over 2. So this will have 1 over 2. Here s plus s will give us 2s. J omega minus j omega will be 0 over there. If we multiply that, this is exactly the same as a minus b times a plus b. That should give us s squared minus j omega the whole squared, right? So here 2 would be cancelled. We have s over s squared. That will be j squared omega squared, and we know that j squared is minus 1. With the minus it will be plus, so we have that, which gives us the Laplace transform of cos omega t is going to be s over s squared plus omega squared. Alright, what about the Laplace transform of sine omega t? So the Laplace transform of sine omega t can be rewritten using that Trig-Euler identity. It will be the Laplace transform of e raised to j omega t minus e raised to minus j omega t over 2j. So because sine omega t is the same as e raised to j omega t minus e raised to minus j omega t over 2j. So that gives us 1 over 2j common. Now we have the Laplace transform of e raised to j omega t. That has to be 1 over s minus j omega minus e raised to minus j omega t over 2 should give us 1 over s plus j omega. So if we simplify this, we will have 1 over 2j. At the bottom we have s squared plus omega squared, as we have already seen, because it will be s squared minus j squared omega squared, and j squared is minus 1. And at the top we have s plus j omega minus s plus j omega, because minus minus would give me plus. So that gives us s would be cancelled here, and we have 2j omega over 2j times s squared plus omega squared, right? So that gives me omega over s squared plus omega squared. And we have here the Laplace transform of sine omega t is going to be omega over s squared plus omega squared. So we have that, and we have that.